All right, so I will tell you about a little bit about this project that we're all kind of involved in, and a little bit about this specific paper. So one question, which as a complexity theorist is a natural question, is how can we prove lower bounds? We really don't know how to do that, so what we do instead is try and think about it in very broad terms, see if there's a direction we can go into. And here's the naive kind of approach to like like a broad way of thinking of how could I find lower bounds. It's the following question. Is there a proof system which is expressive enough to prove lower bounds? Because, I guess the question is, suppose that maybe we're trying to prove lower bounds, like certain lower bounds or new lower bounds that we don't know how to prove. And we want to ask ourselves, what kind of proof, can I say at least something about the kind of proof that would be necessary to do that? And now I claim that kind of the right way of, so kind of the right way of doing this, so of course, we are hoping this is true, otherwise, maybe there's no point in working in our field, right? So, but maybe something stronger even is true, and it's natural to ask. Let me put the word all lower bounds here, right? Is there a proof system that can prove all lower bounds which are true? And I'm going to be vague here, but I'm being vague here for now. But let me try and now suggest what it would be a precise statement along these lines. So if you have a complexity measure C, think of it as, so C of some function, right? So C would be some, if it sets, let's say, functions in a family, right? And if it sets Boolean functions, well, right? So if you put in both, for example, I mean, this doesn't have to be Boolean functions, the argument generalizes. Let's start with that. So, so it tells me what the complexity of a given Boolean function is. I give you the Boolean function as input by its truth table, right? The set of, are you with us still? And it tells me the complexity, right? So think, like things like time complexity, size complexity, of a circuit, space complexity, so on. You could always frame like in this very basic, very abstract way. And for any such complexity measure, there's an associated set, which we call MCSP. Actually, this originally stands for minimum circuit size problem. So the C specifically is circuit size, but now the four letters MCSP are just so in such broad use that we just use them for any model. So the MCSP associated with this particular complexity measure would be, the class, the set of pairs, let's say, of K, such that the complexity of F is the same. And one simple observation is that for any reasonable complexity measure, this problem is in any group. Okay. Why? Because I'm given as input the function f and a number k, and there's a bleep. Oh, it's not bleep. So and some number k, and I can always, for any reasonable complexity model, the size of algorithms is always smaller than twice the size of input bits, then 2 to the power side, and 2 to the power number of input bits, right? So think of circuits. Any Boolean function can be computed by circuits of size less than 2 to the n. Boolean formulas, communication protocols, whatever you think, So what can I do to decide this set in NP? I just guess a circuit, or I guess a formula, or I guess a protocol, or I guess an algorithm of any kind. And then I verify input by input whether that, so I guess an algorithm of size at most k, of complexity at most k. Okay? And then I verify input by input that the algorithm is correct. Right? And because I have this input f, and f is a big object, I can certainly go over all inputs of size of n bits, right? And that's going to take me time. So, roughly polynomial in the size of f. Right? So this problem is in n, and the witness is the algorithm. Right? So now I claim that a reasonable way of framing this question, a reasonable way of formalizing this question is this problem incoherent? So what I'm then asking is there, broadly speaking, a notion of proof? There's several counter arguments against this is the right way of formalizing this, right? But just think very broadly that I could, this proof system could be proofs written, from the axioms of set theory, Zermelo-Fraenkel choice set theory, and you want to prove that the function is hard, and so is there a proof, an efficient proof, let's say, that the function is hard? If there is one in ZFC, then I should be able to verify. Of course, you could argue maybe the proof is very large, but then you're not going to be able to write it down, right? For me, somehow. So, or at least that's the impression that, and this is true essentially for every proof that's known, that for any lower bound that we know that there's a proof and it's short compared to the sign. Right? So, okay. So maybe there will be some caveats, maybe the proof is non-constructive, but then, you've written it down in a piece of paper, and so what do you mean it's non-constructive? You gave it to me, right? When we had a conversation. Anyway, so I think that this is a reasonable way of asking this question. So is there a proof system which is expressive enough to prove all lower bounds, and the emphasis here on the word all, and I think the right way to frame this question is NCSP for a certain complexity measure incoherent?
So here when you say all lower bounds, your emphasis on all is going over radius C, or like
no, lower bounds for a certain complexity measure, right? So the emphasis is going over all f. All f. That's
so when you say lower bounds, it's implicit that you're using a complexity measure.
Yeah, all, let's say, lower bounds for a given C, given a given complexity. Pick some complexity measure that you want to understand, decision trees, whatever. And the question is there a proof system that proves all lower bounds for this measure? By all meaning that for every function f, there has to be, right? So what would it mean for this problem to be incoherent? It would mean that for every function f, there would exist some witness that if it is hard, if it's a hard function, meaning C is bigger than k, right? So right, because another way of asking is this, right? Is this incoherent? Is the same thing as asking is the complement of this set, meaning the set of pairs f k, such that the complexity of f is bigger than k. Is this an n? Right? The same thing, right? So and what would it mean for this set to be NP? It would mean that if the complexity of f is high, there exists some notion of witness that will witness that the complexity of f is high. Right? And broadly speaking, I would say most people in the field believe that this is not true. Okay, and there's some pseudorandom hypotheses that would imply that you cannot. Okay, namely Rudish's conjecture, which we might cover at some point in some others. But for now, it seems like a reasonable, naive, way of formalizing this question. And okay, so there's that, and I should add that, and I'm happy that we have someone present from the Russian school. So Alexei is here, because I should say that there was, so this question of what's the difficulty of this problem MCSP has been studied since the very beginnings of, let's say, theoretical computer science. So the so-called cyberneticists in Russia in the 50s thought that MCSP was the best candidate that they could come up with for a function that would not be solvable without exhaustive search, without, okay, because somehow they feel that there's something kind of self-reflective about this problem. So in modern terms, you could start by asking, and this is maybe the most important question, which is open, completely open in computational complexity. Is MCSP NP-hard? Where I mean the vanilla one for, let's say, circuit science. Even if this turns out, okay, so you know, so like very important question. So okay. So I'm interested in this question essentially because of this. I'm interested in this question whether MCSP is NP-hard essentially because of this implication. Because if you show that this problem is NP-hard, then it will not be in co-NP unless you believe that NP equals co-NP. Which let's take like as a working assumption that it's not. So you know, so having said that, I mean, for this reason, I've been interested in trying to prove that this problem is NP-hard for various complexity measures, and today I'm going to show you the result. So if C is communication complexity, then you know, this problem is NP. This means that, you know, as per this definition of what it means to have, you know, a proof system that can prove all lower bounds, under the assumption that NP is not co-NP, there is no such proof system for communication. So you can see it as some kind of independence, you know, even meta-independence result, conditional. Of course, let me just add a parenthesis here, which is actually, we only really care as people who aim to prove lower bounds one day. We only really care about approximate MCSP, right? Because let's say we want to prove that something does not have polynomial size circuit, right? We don't have to have a proof that, you know, like, first we don't need to do it for every f, right? So that's one thing. But even if we'd like to have a general theory under which we can prove lower bounds, it would be fine if this theory was an approximate theory, as long as it's fine-grained enough to distinguish between, you know, polynomial versus, let's say, exponential, which is what we believe is the complexity of SAT. Okay. But nonetheless, and I will not be able to prove any hardness of approximation for this problem. So I'll be able to prove that the communication complexity is NP-hard to compute exactly. So not even plus or minus 1, I will be able to do. So, you know, it doesn't completely tear down this possibility if you just add the asterisk that it's an approximate. Okay.
So we know that MCSP is
right,
and then to see if it's an co-NP as well. And do we know any larger class of co-NP which doesn't contain NP? Where it's like
no.
That's place we can prove.
No, it's completely possible that it's an NP-hard. So so then the answer would definitely be no. I mean, and for this, you know, for this particular, I mean, it's possible, but you know, people, I'm hoping it's not NP-hard. But most researchers that I spoke with actually believe that it should be anti-hard. It's just a matter of time. And
Something like a BCP or BCP.
what do you mean? Oh,
And
BCP.
do we know anything, whether it's there or not?
No, no, it's not known. Like in quantum algorithms, you said you were suggesting. It's not known. It's not known. Right. So if you're very optimistic, or it depends on what you want the reality to be, but from my point of view, if you're very optimistic, you could conjecture that some approximate version of this is an NP-intersect going. Because that would tell you that there's a proof system, and now you found out what it is because you've proven it's in point B, where you know that if your lower bound is 2, it will be provable here. Because right now, we don't even know what a proof would look like. Whereas if you've managed to prove that some approximate version of this is in point B, at least you know what it looks like. But there are conjectures that have been made by Rudich in particular that essentially rule out that possibility even. So I don't know. So maybe it's not true. This is definitely a result like along the direction that something like this should not exist. Right? Very well. So okay. So let me give you some basic definitions because not all of us have seen this a lot. So now we start. So this is kind of the broad overview of what we're going to do. I should add that this question was asked by Andrew Yao in the very first paper where he defined computational complexity. So it was actually the last open question in this paper. I'm happy that way that we got an answer. So okay. Yes, I should also say this is joint work with Hirahara and Rahul Ilango. Which we more or less finished last year, and it took us a lot of time to write down. Now it's pretty much written down, maybe 2 more figures, and we're gonna put it online. So, all right. So now let's go to the technical. Let's just start with our workout. So, so in this model of communication complexity, what kind of functions are we interested in? I have 2 master students present, so I'm gonna just really review all the concepts, which, so think we have some function from some set, from a product set, x plus y, and let's say it's a Boolean function. I should maybe say some things, like this has been known, for example, for partial functions, that this is NP-hard, but that's very trivial kind of reduction. For bounded round communication complexity, I have another paper with these 2 guys that show that that's NP-hard, and even NP-hard to approximate, there we get hardness approximation. That's super nice, isn't it? So it's really kind of the case that wasn't understood was just the bona fide protocols, which I will kind of say what they are. So in the communication complexity model, okay, we are trying to, for example, compute a Boolean function. And these functions come from a product set. So think of x as being some finite set and y as some finite set. And you have some function, f of x1. Right? And now in this model, you have 2 players. Alice gets some x. Okay? Bob gets some y. And they want to compute f of xy, meaning they both want to know the answer to f of xy. Right? So, of course, if f is a non-trivial function of any kind, they need to communicate somehow, right? So here's how the model goes. Let me draw you a tree because we're gonna look at trees. So, so let me draw like a fluxogram or something of the kind. So at the beginning, the players, Alice gets some x, Bob gets some y. And let's say that Alice starts to communicate. What she has to do, are you with us? So what she has to do is she has to choose a message to send, right? So depending on her x, she chooses the message and she sends. So the first message of the protocol, let's say the first bit, is a function of x, right? And for some x's, you might send a 0, and for some x's, you might send a 1, right? And then they continue. So maybe here it's Alice speaking, or maybe Bob. If it's Alice, then maybe, so if the first guy is a 0, then they agreed, Alice and Bob, and now Alice is again the speaker. And then she must send another message. So in this case, the second message would depend on X, Alice's input, and on the position we are in this protocol tree, meaning on the bits that have been sent so far, right? Whereas maybe here, they decided that it's Bob speaking, right? And then Bob has to decide. So for instance, in here, the second message would be a function of Y and of the position you are in this protocol tree, right? And they keep doing this and so forth and so forth. And eventually this tree is over. And the condition is that once they reach a leaf, the value of f must have been fixed. So how does that happen? So you can think of the inputs as forming a matrix. You have all the x's, one row for x and one column for y, right? And f is some function which I can write as a set of ones and zeros. So it's a Boolean matrix of this shape, right? So at the beginning, Bob doesn't know what x is, what Alice has, knows nothing about it, and Alice doesn't know what Bob has. But now suppose that Alice comes along, she sends a bit. Okay. Then I can put together kind of the x's for which she sends a 0, and I put together the x's for which she sends a 1, and that splits the matrix into 2. Okay. And now Bob has learned. So if Bob has seen a 0, then he knows that Alice's input is one of these. If he has seen a 1, he knows that Alice's input is one of these. Okay. So having seen a 0, he can decide to split his set of y, meaning he sends another bit. For these y, he maybe sends a 0, for these he sends a 1. Or having seen a 1, he might decide to do it in a different way, for example, right? And of course, I'm drawing this contiguously, but these things don't have to be contiguously, right? So it's not like there's an ordering. I choose everything on the left or on the right. It's really actually the subset where to send the 0 and the subset where to send the 1. And here, beneath on this rectangle, the subset can be given, right? Okay, good. And so what's the condition that the protocol has solved the function? So each protocol induces a partition, right? The horizontal splits are Alice's communication, the vertical are Bob's. But in the end, I get a partition of the entire matrix, right? And how can I say that I've learned a function? Is if at each rectangle associated with each leaf, so each of these rectangles in the partition, the function is monochromatic. Meaning it's either all zeros or all ones. If that's the case, then, so once they reach a leaf, I have a combinatorial rectangle here, which is a set of inputs that cause Alice and Bob to reach this leaf, and it needs to be monochromatic on every leaf. Some leaves will be 0 monochromatic, some leaves will be 0 monochromatic, some leaves will be 1 monochromatic. Okay. So a protocol induces a partition. Okay? A protocol induces a partition, and sure.
Is there anything about like how hard it is to decide whether you're sending 0 or 1? So this, for example, is m1 of x. Is there any computational bound on that, or you can do whatever you want? You can have like that.
That's a very good question. So in the communication complexity model, you're okay. This M1, computing this M1 could in general be undecidable. I don't care. Yeah. So it's just a function. So somehow it's a non-uniform model, like a circuit, right? So the non-uniform object, which exists for every n. So presumably this x and y would be families of things which would grow with some parameter, right? And the object that computes it is this tree, which can be non-uniform for every n. And it has a sign. You can think of this tree as a formula. There's actually good reasons to think of it like that. So it's kind of like. So yes, so which means that, and, it's this tree of the functions associated with each node, and those are the objects that define the protocol. They're finite size as long as x and y are finite, right? And that's essentially what we do. As a bit string, if you wanted to describe this tree, how many bits would you need? Roughly, I don't know, something like size of x times size of y, or something times the size of this tree would be n, right? Because to define a function here on Alice, I just need size of x bits, right? To say where you said 0, where 1. To define a function on both sides, I need size of y bits. So this is a rough number, and I have how many nodes. So this is a rough number bounding on the bit complexity of such. And you can show that you don't need more than, let's say, size of x depth. No, even the size of x size. So the size of any protocol is polynomially bounded on the size of the input function or the function input. Right? So NCSP for this class is in NP because I can guess the protocol of size at most k or depth at most k. So communication complexity, right? So I should say that. So the communication complexity of a certain function f is the minimum k such that there exists a protocol phi of depth k or right. That's the communication complexity. That's the measure that we're looking at. Right. And because so Alice can always just index the entire x and then bubble the answer or vice versa. So the communication complexity is looked at most. How many bits I need to send x? So we log type of x. At most the minimum of this value. Right, so these objects are finite. If to prove that this problem is in NP, I see that the objects, the protocols can never be very large. So I can just guess the protocol and check if it solves that. The protocol is just a tree. Is a tree together with the functions that send the bits together with the monochromaticity handle, which actually I should be able to use that for math.
And you can dig up this function to specify two tables about like the complexity of each function.
Yes, exactly. Yeah. So it's like a truth, for a communication problem, this is the truth table. Good. Stay with us? All right, good. So now the question, of course, is now, how do you prove that this is NP? And I should say that the three of us have tried for many hours and completely failed. And then eventually we came on this paper of Jiang and Ravikumar, where they had something that looked like it a little bit. Tell me what that means. I need to define this thing, which is called high-order. It's a different computational complexity measure. It's called the one partition number of the function f. The one partition number. Okay, so it comes from the following observation that you could get at this measure, right? So a protocol divides the matrix into rectangles. And now if I take the one monochromatic rectangles, they form a partition of the ones. Right? So I could just generalize the measure and just say, this is the minimum. Is the minimum number of rectangles in a partition in a rectangle partition of the ones. Right, so, so for example, I could just take one rectangle for each one in the matrix, right? That's like the worst that I could possibly ever do, right? So if I do that, so now I know that pi1 of f is at most size of x times size of y, or in fact, the size of the set, right? But it could be a lot smaller. Like for example, if the function is all 1, 0, and all 0, 0, I just have one rectangle for the ones, and that covers all the one. That partition is all one. Again, by rectangle, if you're not used to this terminology, I think I told you to see some lessons in communication complexity, but it's just a subset of x times a subset of y. So, all right. So now, so this is some number, right? So I need at most size of x times size of y, and I need at least 1 or 0 if there's a 1. So it's some number. It's the minimum number of rectangles in a partition of 1. And these two guys, Jiang and Ravikumar, had it turn out had shown maybe give me the date also. You get an idea. I think it was 93. 93. Pi1 of that is a pi. Although it was a bit of a stroke of luck to find this because their proof doesn't look at all like a proof proving this, but what it actually proves in the language of communication. So it proves something else. So I can even tell you the name of the thing. So right. So they actually showed for some problem called the normal set basis problem that is NP-hard. And it turns out that this is exactly pi1 for some reason. Exactly. No, exactly. Like to the t is the number. It's just a different way. It's a different language to talk about the same quantity. So we somehow stumbled upon it.
The normal set.
Huh?
What did you say? The normal set.
It's called the normal set basis problem. Set basis. All right. So instead of telling you what the normal set basis problem is, I kind of forgot already at this point. I'll just do, so the first thing that I will do is I will do you their reduction, because that's essentially half the paper or maybe more. And then from there, we'll try to slowly massage this into an NP hardness proof for communication complexity. Okay. And their reduction is really gorgeous. I mean, we worked for hours trying to get even the smallest improvements or smallest add the new idea, and we weren't able to do that. So because we were trying to get hardness for approximation, and it's nothing. I mean, it's even somehow surprising in the end that you get hardness, because it's like you squeeze it through the tiniest hole, and I can find no possible improvement to the argument. So, all right. So I'll just present it to you, and I think it's like really, really good stuff. So, okay. All right, so I want to show this problem is NP-hard, so I'm going to do this via the vertex cover problem. Okay, so let me tell you what the vertex cover problem is. Vertex cover. So I'm given as input a graph G on n vertices. Under X graph G. And a vertex cover is a set of vertices that cover all the edges, meaning for every edge in the graph, there exists some vertex in the cover belonging to the edge, meaning V is one of the two vertices in the edge, right? So you have a graph, you have vertices, you have edges. A vertex cover is a subset of the vertices. So in this case, for instance, this, such that every edge has one endpoint in this set. At least could have both, but has at least one. And I want to output in this problem the minimum number, the minimum size, and let's call this kappa of G, or K of G, minimum size K of a vertex cover. So it's the smallest number of vertices that I need to cover all the edges. That's the cover number of the graph G. Okay. Now, so this brought class. I think this is known since should have it here, but I think Carp proved that this was NP-hard in this
One of the original
21, right? So Carp 79 something.
Samsung run this video. On,
Say again. Oh, the video has stopped.
yes, video stopped.
Yeah, it did for me too. For it was my internet connection at first.
Okay, but you can hear the audio still, right? So let me try and restart the video. Stop video. Yes. That's not nice. Okay, let me try and. Oh, now it's good, no? Yes.
Yes, yes.
So, and Carp has proven very shortly after Copenhagen results that this problem is NP-hard. Right. And now let me show this. So let me use this to show you that computing chi1 exactly is NP-hard. In fact, there is even some hardness of approximation. There's even some, I should have the names. Somehow I should have them here, but I don't, so I should add that. I don't remember who proved that this is hard to approximate, but it's hard to approximate. I forgot. There's a bunch of people, I think, but who was the last person? I forgot. So this is NP-hard to approximate up to a factor of what? Was it 2 or was it root 2 or something? Up to. Oh no, up to 2. 2 is possible. 2 is possible.
Yeah,
2 minus f?
yeah, take the whole set of terms.
Oh, that's
Based on unique things. 2 minus.
2 minus f. Okay, 2 minus epsilon is on unique games conjecture. And no known is like root of 2 or something, or root of 2 minus epsilon or something.
Wikipedia says 1.36.
Or 1.36. Unconditionally. Okay. And can you tell me the names? I might as well.
Dinner and Safra.
That's the unconditional or the
Unconditional.
That's unconditional. So that's Dino and Safra.
Well, there's a better one, but Wikipedia is not rendering it in math text. There's something better than that.
All right. And this is what clock or something. Okay, fine. Okay. We're actually not going to use this. I'm just mentioning it so that you know, we could have used it to get a little bit of hardness approximation, not for the communication complexity, but for the size of the protocol. Because when you do a log, right, you lose this. I mean, you have 3, maybe you could have plus or minus 1, but when you do a log, you just have a factor of 2, doesn't matter. So, all right. So now let me show you Jiang and Ravikumar's results that say that chi1f is NP-hard, and it's by reduction from vertex.
So you're saying chi1f is hard to approximate?
Chi1f, Nuremberg, yes, up to some small constants. I think that's true. It actually depends on the number of edges, but I think that the number of edges in these things, when at least I think it is linear in N, and in which case, then it will be NP-hard to approximate for some smaller constant than 1.36, but some bigger than 1. Right. So this, yeah, right. So yeah. But the thing is that chi1 is like the CC is like log of chi1. So because the constant is not 2, and you lose it, right? So it doesn't. Okay. So let me give you like their clever construction. So now what do I have to do? Right? I have a graph G on n vertices. I want to convert it into a communication problem, FG. Right? And the partition number, the one partition number, chi1, this FG, should tell me what kappa of G, the vertex cover number is. So now let me tell you what the rough idea is. So, so somehow I need to, I want a gadget, right? So I want some gadget which represents the choice of the vertex being in the cover or not. And this choice should somehow be translated into how I cover my ones by rectangles. Right? So let me tell you how that choice happens. So I'm now drawing you the communication matrix of X, the 0, 1 matrix of X. It'll essentially have 2 parts. Maybe I should draw it bigger. Okay, so here I will have 2 n rows and n columns on this part here. And here I will have 4 sides of the number of edges rows, and here I will have 5 number of edges columns. So that's what the communication matrix looks like. And okay, so I have 2 n columns, meaning for each vertex, let's say I have 2 entries, right? So I have for vertex 1, I have entry 1, 0, 1, 1, etc. up to vertex I 0, I 1, etc. Now I have some other vertex j, j0, j1, etc. up to n0, n1. Okay. And I have n columns here, 1, I, j, n. And this part of the matrix is just kind of this double diagonal. So I have 1, 1 here, and then 1, 1, and then 1, 1, 1, 1, 1, 1. And that's what it is. Okay. So now notice that there is now a basic choice that I have to make when I'm trying to come up with a one partition for this matrix. This is even without thinking about what the rest of the matrix is. So I'm trying to now partition these ones into rectangles, right? I mean, these different ones I can never put in the same rectangle because the off diagonal entry is 0. So whenever I don't draw, it's 0. Okay. So this one cannot go with this one because this is a 0. That will be bad. So it wouldn't be monochromatic, right? So okay, good. How about among these two? Among these two, I have 2 choices, which is I either put them together in the same rectangle, or I put them separate in 2 different rectangles, and that will increase my partition size, right?
So a rectangle doesn't have to be contiguous rows or columns.
No, it's a so-called combinatorial rectangle. Meaning, so combinatorial rectangle is a subset of the rows and a subset of the columns. We take the products. They don't have to be contiguous. All right. So okay, so the basic choice of whether a vertex is in or not the cover that I'm so now what will happen, right? How will the proof go? I will have to argue that first I have a partition whose number, the number of parts, is related to the cover number, and vice versa, that any partition will give me somehow a vertex cover. So I have to extract the vertex cover from any partition. And this is how I do the cover, right? That's whether the partition puts these two together into the same rectangle or in separate rectangles. That's how it's done, right? Okay, good. So how about the rest of the guy? Now we can try and think like, well, you know, it's clever. So okay, so now what's the idea? So now I have these two vertices, I and j, right? So now I have this edge gadget. Let's look at the edge gadget that corresponds to a hypothetical edge ij, which is in the graph. I will have here 5 columns. 5 columns. 1, 2, 3, 4. 1. If the edge is edge ij, everything will be 0 kind of in this square, in these columns, except for these 4 rows. And then I will do it like this. If I is the smaller number in the edge, I will do it like this. 1, 1, and everything else. Now, okay, so that's part of the gadget, and I can explain to you, the functional idea behind this part of the gadget, which is the following. If I put these 2 ones together in my partition, then I cannot use this rectangle to cover any of these because these guys are 0. Right? Whereas if I put these 2 ones in separate rectangles, I can also, might as well, add this one to this one and this one to that at no extra cost. Right? Okay, so now how can I use this? Now is the really clever part. So now I have 4 rows here. 1, 2, 3, 4. And I just do like this. So 1, 1, 1, 1. For these 2. These are aligned. And on the other 2, I crisscross them. So I have like 1, 1, 1, 1. And here I have all 4. So now let me tell you the idea of the proof. And we're going to prove it like rigorously, but let me just.
Is there anything on the bottom left?
Everything else in the matrix is 0.
The bottom left?
Is 0. 0. Everything that I didn't draw is. Okay, so now let me tell you the idea. The idea is the following. Look at this guy. I have to cover these 4 ones, right? Essentially, there's, if I want to save on the number of rectangles, there's kind of 2 ways of doing that, which are smart, which is I take these 2 ones together with these and these 2 together with these. Right? I take these 2 ones with these and these 2 ones with these. Or I choose the other 2, these with these and these with these. Right? And that will allow me to cover 3 of these columns using 2 rectangles. Which is good. Okay, however, I'm in trouble. Suppose that none of these ones were covered by these rectangles. I'm at a loss how to do that now because, I can either spend my budget covering these guys, or I can definitely put like this together with this. But if I do that, I cannot use these 2 to cover these 2. Right? That's the basic idea. I told you the whole gamut. I told you the whole gamut. Now we're gonna do it carefully, but that's the basic idea. So suppose that I have a vertex cover, right? So that means that for every edge, ij, either I is covered or j is covered. Right? If I is covered, these two are separate. So I can say, I can use the same rectangles, the same two rectangles that cover this, to cover this also. But then I don't need to cover these anymore. I think maybe everyone understood, so maybe you understood. But this is like crucial. So if these two are separate, I can cover these two. So I don't need to worry about these two anymore. Then I can use these two for this and these two for that. Right? So if these two are separate, right, I can use them to include these. So I don't have to worry about them anymore. They're covered. So I can use these two for this part, and I use these two for this part.
So the three that we were covering at the bottom, you were covering 3 columns with 2 rectangles.
Say again?
There were 2 ways of covering 3 columns with 2 rectangles.
Yes. I either use these two for that.
These 2 for that.
I either use these two together with this, or I use these two together with that.
I guess it is there.
Exactly. So the guy that didn't get covered by the vertex cover, I have to use these bottom ones to save on that one. But I still have the other 3. If it's a vertex cover, I still have the other 3. If it's not a vertex cover, then I'm in trouble. Right. So that's the idea. So now let us do it kind of carefully. Let us do it carefully. So what we're actually going to show is that for this function, this equals n plus 4 times sine of b plus cover number equals b. That's what we're going to show. And let's start with the easy direction, which is the multiply. Right? So what does that mean? That means that I have to find a cover, a one partition using a vertex cover for G. Right? So here's what we do. I've essentially told you already, but let's just go over it again. So take any cover, right? Take any C minimum cover of the graph G. So the size of the cover is the cover number. Right? So here's what I'm going to do. I look at all the vertices. If a vertex is not in the cover, so for example, if J is not in the cover, I cover these two ones by this rectangle. If I have a vertex which is in the cover, then I use 2 rectangles, namely, maybe let's do cover it now. Then I use 2 rectangles, namely this one and this one. So these are on top of each other. For now, that's right. So good. So far I have spent right, it's 2 sine of C plus and minus sine of C. Rectangles. Right? Okay, so now I need to do the edge gadgets. So I don't look as often. Are you guys following? I don't look as often to the thing. It's just this problem. Are you good? Any questions? Sorry, I'm talking. Any questions?
It's good. It's good.
Yes. Okay, so now how do I cover? I also need to cover these, right, by my high 1 partition. So, but now I know, because this is a vertex cover, I always know that when I look at this gadget, either this one is taken care of by I, or this one, or these 2 ones are taken care of, right? So, but now how do I do it? So let's suppose that I is taken care of by this rectangle, this pair. Then I can just do, so this would be 1. This would be another one. And, you know, like, this would be another rectangle. And this would be another one. Four. Yeah, percent. 4. 1, 2, 3, 4. So in total, I have spent these many rectangles as promised, right? So that's the upper bound, which tells you the idea of the reduction, and now you have to prove that it actually is the best possible. There's, you know, you can't do anything better. Right, so for the other step, so now we want to prove that this is so, you know, okay, take any, let's take any one partition of N. All right, so okay. So this partition must cover all the ones, right? So in particular, it covers these ones. So let's call the rectangles that cover these ones, let's call them node rectangles, meaning node for node in the ground. Okay, so let C prime, let's say, be the set of I such that so you know the entries I 0, I, and I 1, I are placed in different rectangles of human position. We're just kind of going back. Right? And now we want to claim that this is a cover. It's actually not exactly, it's almost going to be. So, so now let's see how many rectangles have we accounted for. There are at least, so we have so far counted for n minus side of C prime plus 2 side of C prime rectangles. Right, just to cover these, what I mean is just the rectangles that cover these, well, they're exactly these many. Now claim. So now one issue in trying to prove that you know you need at least this much to cover. One issue is that the ones that are here, right? So the vertex I belongs to several edges, maybe, right? And now the question is, could you maybe use these ones together with the other edges to say? And now, so here's this claim. Right. Then we can assume, but without loss of generality, we can assume without loss of generality that if a vertex I has not been placed in C prime, right? So if it's a vertex like this, then none of these ones go together. I think that's what we have to get here. Right?
Yeah, if it has those together, then that rectangle is done, right? You cannot just add anything further.
Exactly, yes. That's exactly how you do it. So if I, yeah. So the thing I'm trying to avoid is saving up on a number of rectangles by putting all of these ones together. But now I claim that if I have a partition, one partition that's given that does that, that puts these two together. Put this in there. Then I have a partition with the same number of parts, same number of rectangles, where these two have been separated. So if I has not been separated, then you know, like let's say, for example, this column would be like I0 J, and now imagine another entry for some other J prime, I0 J prime, do not belong, do not share a rectangle. I can assume that. Here's why. Here's why. Suppose that I have a pair, you know, some guy which has been put together in the same rectangle here, but such that this one and some other one belong to the same rectangle. Now, because these two belong to the same rectangle, like Diogo was saying, there can be no other row. There can be no other row in this rectangle because everywhere else you have zeros, right? Or rather, you know, like maybe here you have a 1, but on the corresponding for J prime is a 0. So I cannot add any other row to this rectangle. But if I cannot do that, that means that the rectangle is completely included in the row. I may as well split this into two and put this one together with those. And I have not spent any more rectangles to do that. Right? So as long as this condition is violated, I just keep splitting the i's until it's no longer violated, and I have not increased the number of rectangles that I've done that I needed to do that. So okay. So now let I guess one right. So okay, so now I want to pretend that this C prime is a cover, right? So let's look at the edges that are covered and the edges that are not covered. Let's say that E1 is the set of uncovered edges. So it's the set of edges such that I has not been covered and J is not been covered. Right? And let's say that E2, you know, is the red. Because these are the edges that have been covered. Now I claim that each edge in E1, in the gadget for each edge in E1, I must have 5 rectangles. Otherwise I can't cover the one. Cover all the ones. Right? So what the edges in E1 are such that these two guys were put together and these two guys were put together. So, but that means that I can't use this rectangle or this rectangle to cover any of these, right? But then all of the ones in the gadget need to be covered still. Now, there's a pooling set here, which is I can just take this one, this one, this one, this one, and this one. And it's a pooling set of type 5, because, you know, on one of the corners, I always have a 0. Right? That means that I need 5 rectangles to cover. It's a set of 5 things, and like, you know, it's like the top diagonal of this thing, it's all zeros. So I actually need at least 5 rectangles. So that means that I can account for at least 5 and size of V1 more rectangles. How about these guys? How about E2, right? So the edges that maybe were covered maybe by one, maybe by both. Well, I still need to cover these ones, right? I have to count this, and these ones cannot intersect these ones, right? So that will mean right here. So sorry, I kind of skipped the step, which is a bit subtle, which is that I'm using here that these ones cannot go with any others, right? So because for vert, right? Where am I using that?
You still need to cover all this one.
Yeah. Yes, exactly. So these two are put together, right? So by our assumption, these ones are not shared. They don't share a rectangle with any of the other ones, right? So these guys have to be covered by separate rectangles for every edge. So that means that every edge gadget needs to be covered by separate rectangles, right? These parts are disjoint, right? They're diagonal among the edge gadgets. These are not, but by our assumption, they don't share a rectangle, right? That's why I can get 5 rectangles out of each edge. Without that assumption, so I've used that assumption here, right? Without that, oops, they could match, right? So, okay, so all I need to account for is the rectangles that cover this part, right? And well, it turns out that whether they share with these ones or not, I actually need 4 to cover this. I cannot cover this thing without 4, which we can see by having like a full set, I guess, something like this, and this will do. Okay, so I also can account for at least 4 sides between rectangles, and these rectangles that I've accounted for all have to be different, right? Okay. So let's see now. So what do we have? We have in total we've accounted for n plus 4 sides of E, right? Plus size of C prime plus size of P1. Many different rectangles. But now look, I can actually make a cover. Now that everything is set down, is settled, I can actually make a cover of this side. How? Well, I just put these guys in the cover, and they will cover all the edges in E2, right? And the edges in E1, well, I have as much budget to choose vertices as the number of edges in E1. E1 vertex, one area. I'm just looking for the vertex variation. So so this thing is at least. And that's the proof. That's the proof. Well, it's not translated from whatever they were doing. Good. Clever. That's good.
Yeah.
Good, John Robin. I bet you can be wrong. I will need this. All right. But that's not what we promised, right? So we promised that communication complexity is going to be hard. And although there's some relation between this and communication complexity, this Pi1 and communication complexity, it's not the same, right? In fact, there's separations of these two. of these two notions. So there are functions where it's not the same. And I would kind of want to argue that for this particular function, we are still more or less in good shape. And for this, and now it's just a bunch of tricks. Proof on top of this reduction, it's a bunch of tricks, observations. You have to be carefully fine-tune it, and you get communication complexity. So let me tell you. Great. So let me first make the following observation, which is actually kind of the turning point when we're looking at this, which is the following. This protocol, this function, f of g, I can actually solve it by a protocol which is almost balanced, meaning where the communication complexity, the depth of the tree, is roughly equal to the number of leaves, say. Log the number of leaves. Right, so the depth of the tree is roughly equal to log the number of leaves, which is what you need, right? Because somehow chi1, right? So you have this like the communication complexity of any function is at least log of chi1. Okay. Right? This is obvious because you know, the protocol itself gives you a one partition, right? And the size of one partition is at most 2 to the depth of the protocol, right? Because the protocol splits, right? Each protocol induces in the communication matrix confirming partition, and the leaves where each rectangle in the partition is a leaf. And if you just take the leaves that are one monochromatic together, they form a partition of the entire matrix. So, and how many leaves do you have in a rectangle in a tree of depth d, at most 2 to the d, right? So chi1 is at most 2 to the communication complexity.
You can have rectangle that comes provide this, you know, this nice partition that you split.
Yes. The other thing is not true. Okay, so each protocol gives you a partition, but not every partition is a protocol for. There is some relation, so there's some lossy relation. There's something you can say in the other direction, but that's tight and there's a loss. Okay? It's quite a amount. In the logic line. You can get a square. If you want the other direction, you can get a square. And that's fine. But okay, but you know, so this is at least, but I've proven that this is chi1 is NP-hard. It's a bit tricky, right? Because I've proven that chi1 is NP-hard, and now you have this log and this ceiling, and you know, how do you do it, right? So, right. So okay. So the first thing to observe, you know, but so the idea would be that, you know, if F has a balanced protocol, then the communication complexity is really roughly like log of the size, log of the number of leaves. If F has a balanced protocol, right? Not all Fs are going to have the opposite equality, because we want to prove that for this particular F, it's roughly true. Now you want to tweak it a little bit until it's exactly true. Right? But let me show you what the protocol is. I want to draw it. So here's what the protocol, and I'm going to give you a protocol which isn't even binary. So I'm just giving you a tree where I say Alice Bob speaks here. I'm not going to worry about the matter of bits because they're sending bits. I'm going to worry about that after. Okay, just for some time. So at the root of the protocol, Bob will tell Alice 0 or 1 whether he has one of these two columns. I'm going to draw it like this. Whether Bob has one of these two. Now this step has to be chosen very carefully. You know, NFCD, I call it. NFCD. Stands for you know, not first cover vertex. not first covered vertex. And the idea is the following. This could be either 3 or 4 for a particular edge. This could be either 3, 4, or 1, 2 columns. Okay. And when is it? So I look at the 2 vertices that belong to my edge, yes. And if I is in the cover, so fix any cover, right? So this circle depends on some cover that we fix, right? So if I is in the cover, then I want these 2 columns. If I is not in the cover, because the cover is a vertex cover, then I want these 2. Okay. Or maybe not. I guess first is maybe necessary. It's not covered, right? So
both vertices are covered.
Then yes, if both vertices are covered, then this one is exactly so not first. Right. So if both of them are covered, which is totally possible, then I do 3, 4, because J is not the first cover. So for each edge, so it's like so what's the column? It's and now it's how to translate this. It's complicated, so for each edge, you have ij, right? Oh, I see. So I want, yes, there's a set of columns, the I, j, 3, 4, 3 and 4. So the C, if I is in the cover and C and is in the cover and C is either 3 or 4, or I is not in the cover and C is either 1 of them. So this is a set of columns, right? So I told you how to choose them. You go over each edge gadget. If I is in the cover, you put these 2. If I is not, then you put the first 2. And you do this for every edge. This is a set of columns of ball.
Can you do a step back?
Yeah.
You have this entire matrix, right?
Mhm.
And Bob could have a column that is neither 1, 2, 3, or 4.
It could have some of these.
Have some of those, right?
And then I'm going to go on this side. Right? So I will send you a 1 or a 0.
Yeah, similar for Alice, right? Alice could have like something on the top. Half the matrix, but she could also have something on the bottom.
Absolutely. I mean, she could have any of these rows. And Bob also. So I've selected some of the columns, some of them. And the first thing that Bob says is 0, 1, whether he has one of these. Right? So here you have the special columns in NFCV. Right? And here you have all other columns, including all the other edge columns and these. Now, if he does have a column in NFCV, so this would be a Bob node, then Bob will say which. And I believe he says exactly which. Which column? Which among the columns in NFCV? So Bob will say that. So I'm not thinking of binary protocols yet, so I can just think that there's a node here and there's like an edge outgoing for each possibility. So how many possibilities do I have? I have 2e, I guess. Right? So the number, the fan out is 2e. Good. And if Alice knows in this now let's continue here. Now if Alice knows precisely which column Bob has, she can just say 0, 1, whether that entry for her row is 0, 1. So here we can. Or not. Huh? No, what do you mean? Wait, we haven't done this side yet. Oh, but that's Bob. Oh, so this is Bob, these are all Alice. Awesome.
Right, so this one is possible Alice has a vertex in the row in one.
A row in what?
The bottom one.
No. At the beginning, Alice can have any row, then Bob speaks. then Bob speaks again, she could still have any row.
But at this point, Alice knows exactly the column that Bob has.
Yeah, but at this, on any of these,
It's not telling which in the.
Yeah. No, sorry, it's just the answer, right? So for instance, if it turns out that Bob says, I have this column, and Alice is here, she says 0, if she's here, she says 1, if she's 0, 1. Okay? It's the output of the, not you, because she knows Bob didn't, but. Good, okay, so how about the other side? Now, the other side is again trickier. It's again trickier. So there's a few cases. That sentence that everyone dreads to hear when they read a book. But yes, but it's okay. But the kids are not too far. So essentially, so you know, how do you find this? You kind of understand that something here has to be special, right? Because on the upper bound, you know, sometimes these are matched above and sometimes these are matched above, right? So these were the ones that you, let's see, I is in C, so that you maybe could not match above. Right? That you maybe meaning, right, so that, sorry, that maybe these are the ones that you maybe still need to cover by those, right? So that they're special in that way. Right? Because if I is in C, these are covered, so I don't have to worry, but maybe I have to worry about these. So these columns that XDV are the columns that maybe I have to worry about. So the first thing Bob says is, do I have a column that maybe we have to worry about or not? Kind of makes sense in that, right? And then for the rest, it's kind of obvious. We just kind of follow the strategy, right? So what does Alice say? She will say, she'll kind of tell what situation she is in, right? So if Alice has one of these two, where one of these I0 or I1, where I is in the cover, she'll tell Bob exactly which I0, I1 she has. So that costs you like, you know, let's just think that, you know, so I split this tree into like 4 cases. And the first case has fan out 2 sides of the line. So if I have a vertex, if Alice has a row, which is a vertex, which is an I0 or I1 for I in the cover, she'll tell Bob which I0, which I1 she. And that somehow there's 2 sides of C, many rows like that. If she has a row, such that, okay, and you can see that Bob now knows the answer, right? Because now you've reduced it to a single row, so Bob knows the answer. And it will always be, so Bob will always know the answer. Now suppose that Alice has a vertex which is not in the cover. Then what she will do is she will, like, she has J0 or J1 where J is not in the cover. Then she will tell Bob J. She won't tell him whether it's 0 or 1, she'll just tell him J. That means that the message that Alice sends partitions the rows and these two get in the same part, right? But now look here. On this side, we're guaranteed not to have these columns. Right? So they have disappeared and they only exist on this side. That means that on both of these rows, if I look at any column, it's the same. It's either 1, 1 or 0, 0, 0, 0, 0, 0, 0, 0, 0. These don't belong there, 0, 0, 0, 0. Right? So Bob also knows the answer. Now, he might not know exactly which row Alice has, but he does know the answer. So the answer. So, and that costs you n minus sine of c. Width here on the bottom. Symmetry. Like, so what's the other case? The other case is Alice has either one, you know, like, you know, now like you have to see, like, suppose that, you know, this somehow the bad columns are these, then Alice is going to group these two together. Right? If Alice, now what's the, okay, so I told you what Alice does on these rows, and I only need to tell you on the edge gadgets. Right? If she has an edge gadget where, you know, like the first guy's in the cover, then she will tell Bob whether she is on which edge gadgets she has, but she doesn't distinguish between 1 and 2. And she doesn't distinguish between 3 and 4. So she breaks it like this. If on the other hand, it was J that survived, right, she would break it like first and third, second and fourth. And what happens is that Bob now always knows. For example, in this case, right, so this is broken like this. And again, it happens that on every column, either both rows are 1 or both rows are 0. I'm basically trying to turn the strategy, previous strategy, into a protocol the best way I can. Right, so this will, I mean, the fan out here is like 2 sides of E, right? 2 sides of E. No, wait, if I missed something? Sure. Oh, no, yeah, sorry. 2 sides of E, 2 sides, right? Sides of E here and sides of E. Sorry, it doesn't matter, right? So this would give me E possibilities, and these two would give me E possibilities. Okay? So in the end, the total fan out that I got on this thing was, n plus either 2 sides of E plus either 3. And the whole thing times 2 if I want to count the numbers. Good. So, okay, I told you a protocol. There's a few issues. One of them is that the protocol is like non-binary, right? So, I'm worried about the problem of converting this thing into bits, right? And I will postpone that problem for now. But if I try to count the depth of this protocol as if it was a binary protocol, like, the fan out here is this, so let me count this, the depth here as ceiling of the log of this, right? So then I get, on the left side, what's the depth? Is 1 plus ceiling of log of this. Plus 1 at the end, right? And on the right, I have even less. I have 1 plus. Oh. Good. All right. Okay. So now, right. Good. So So what now? Now the idea is the following. I want to pad. I want to add. I want to now change my FG so that if the cover number is small, I can fill this tree exactly tip top until it's completely full binary tree. But if the cover is large, I'm gonna have an overflow of height, and I get one more bit of communication. That's it. Okay, right? So right. So currently, right. So currently, the height of the tree.
We're trying to make n equals to E with a small number of to the end, or to the something.
Yeah, exactly. So what I do is, so I'm given G, right? So I don't know what the cover number of G is, right? But here's what I know. I know that I can assume that it's either small or not small. So it's either less than K or bigger than K, right? So, and what I want is, I want that if the cover number, so let's say, I'm given a graph G and a number K, and I want to decide whether this is less than K or bigger than K. I think this is actually the problem that I kind of solve. Which is often hard. Right? So what I'm going to do is, so I have my FG. I'm getting tired. I have my FG. And I'm gonna construct a function fg prime, where I append, so this is like 0, 0, and here I put an identity, like, 1. So this is the identity on, let's say, d by dn. Okay. And I'm going to choose d to be the number which would be missing here to make this a complete binary tree, assuming that the cover number is at most k, right? So I assume that the cover number is at most k, and this gives me some size for this protocol. This protocol might not be complete, right? But now I actually am not looking at FG, I'm looking at prime of G, where I've added exactly as many ones as I would need here, so that this tree would become a complete binary tree if the cover number is at most k, or if the cover number is k.
What is this computation to be done on both? Oh no, only on. So Bob would send one. With one of those columns.
Yeah, yeah, exactly. I mean, somehow, but so I am looking at the shortest protocol. So the shortest protocol will distribute these d in the best way it can to minimize the height. Right? So what I need to do is I need to choose d so that if the cover number is at most k, I can stay within.
So you're just making it like incrementally harder until you is that how it's supposed to be?
Let's just solve this problem, right? So if the k right? Then what do I do, right? So I have a certain number of leaves here, which I have yet to count, but we can count them. It's I have exactly 2n plus 4 not 8, yeah, 4.
Oh, you're counting both together.
No, yeah, but you also split in the end, right? So plus 8, I believe, or something.
4 from the left, 4 from the right.
4 from the left, 2 from the right, times 2, because of the last split. Plus 2 times. This is the number of loops, right? There exists a power of 2, right? Plus c plus 2 times of c. So now I choose a power of 2 so I'm now given g and k. Yeah, you do this. Please. So I choose the right. So let L be such that is that most, let's say n well choose that you plus. I choose this number. So it's the number that just because this is forget about the factors of 2, this is just like plus 1 or minus 1 on the log there. So let's just say L is it. Okay, so it's the first power of 2 that's big enough hold this number.
What about forgetting the 2?
I mean, I could put this here. I'm just copying from here. So I could have put this multiplied, but then it would just be choosing L plus 1 instead of 2 becomes 14.
Yeah.
Yeah. So what I want to say is that once I'm now going to have a matrix so that essentially L is actually the right number.
Shouldn't it be 40 because we're dividing by 2?
Here.
Or is there no?
No, I think not, because I'm thinking, so this is the number, this is the fan out here, right? And I want the fan out on the right to be the same. So I just take the biggest of the two values. So, right? I take the biggest of the two values, I find the power of 2, which is just above it, not strictly, just above it. And then, so I'm going to add as many ones as I need so that if the cover number is at most k, I can do it by, or even if it's up to k, I can do it by a binary tree, which will never be bigger than some number, which is going to be L plus 2, of course. But if the cover number is actually large, I have to take over to L plus 3. I need one more. You know, so it might only be just a little bit more that I need, but I will need that little bit more. And so the communication is going to be bigger. So that's kind of the crux, like how to. So to convert kind one into this, you first have to see if the protocol is balanced. And once it is, you can adjust it by padding the matrix so that it's not only almost balanced, it's actually really balanced so that it's right at the edge. So that if actually the cover number is large, you're going to have to step over the edge and communicate more. Right, so that's the idea, and you kind of have to work out what the calculation is. So somehow, let's just take this, right? And it's not going to be L. The communication is not going to be L with L plus 2, right? It's 1, 2, 1 L plus 2. And if the cover is large, I want to prove that it's at least L plus 3. Right? So I just take L to be this, the first power proof big enough to fit this. It also fits this number, right? So now, you know, let's say D0. D0 is 2 to the L minus the thing that I'm assured that I'll have there, which is n minus 2 times v minus k. What is D0? D0 is the number of leaves that I'm missing here to make a full binary tree of that L. And D1 is going to be the number of leaves that I'm missing on this side. Okay, so that's going to be 2 to the L minus 2 times v. And D is the sum. So the identity D is D0. So now the actual function in my reduction is going to be this f prime v. And now I want to prove two things that if the k of g is at most k, right? So if the cover number of g is at most k, then the communication complexity of f prime of g is going to be at most L plus 2. But if k of g is bigger than k, then the communication complexity of fg is at least L plus 3. That's what I want to do.
I have some. I'm just worried about something, but maybe it's because it's not like computational complexity, but communication complexity relation. It's that in this construction of f prime g, you kind of need to know the value of k, because you need to know the value of c to say how many.
Yes. No, but this k is not the true complexity of the graph. I'm just given as input. So here's the complete problem that I actually start with. I'm given as input some graph and some number k, and I want to know if the cover number of the graph, vertex is at most k. Right, this is the number that I used. And I believe that this is the number. Yeah. So we actually know the value of k.
So this k is not the value of f in.
Yes. So this is what I do. And kind of, okay, so now, okay, so let's suppose that the cover number is at most k. Really. Then let's look at this program, right? I can actually, you know, it wasn't binary, but I can make it binary. Now, because right, this, so I append here another case, which has D0 possibilities. One, I just choose D0 of these guys, right? And Alice sees, oh, if I have actually one of these extra rows, I will just, when I come here, if I have one of these extra rows, I'll just tell Bob exactly which I have. That gives me extra D0 there. And Bob, in this case, if we end up here, Bob is going to say, if he has one of these extra columns, right? So if Bob has one of these D1 columns, then he will say exactly which one he has. So maybe that's my. And now both these subtrees have the same size, so you know you're expecting one. But again, it's not now, right? So I've proven that you know k is at most for if complexity of b is at most k, indeed I can come up with a protocol whose communication complexity is at most L plus 2. Right? Because it's one bit, then exactly L, because I filled the binary tree, and then another. So now, you know, and then you're doing this, and you're hoping that, well, can I prove the other thing? And now you stumble into a problem, which isn't a big problem, but at first it seems a bit daunting. Which is the problem. Okay, so now how do I prove the matching lower bound? So somehow I have the upper bound, right? By what is reduction? Upper bound. So now I have to go match lower bound, and you know, what are you gonna do? It turns out that you do it via the chi. Because chi behaves nicely under this. Right? So you just add exactly, you know, whatever chi you just need is diagonal matrix, right? So that means that if k of g is at least is bigger than k, then phi 1 of f prime g. Now I have to think, right? So to cover these, we know how much we need, and then it's plus d, right? So this is at least, in fact, it's going to be equal, but we care about is at least. You know, and right, n plus 4 times d plus k, bigger than k, plus this number d, we added it with, right? And now, you know, we've chosen d to exactly, you know, replace this thing with like L, right? So this is equal to 2 to the L plus 2 to the L plus k. Right? 2 to the L plus 1 plus k. And you come to this and you despair because, all right, so let me use the default lower bound, which is that the communication complexity of this thing is at least ceiling of the log of phi 1 of f1 g. That, right? What is that? Well, ceiling of this log, I have, this is the power of 2, right? It's L plus 1, so I'm adding something positive, so I get L plus 2, which is shit, because, you know, it doesn't seem to distinguish it. But actually, magically, it turns out that this is actually, which is less obvious, but actually true. As long as f prime g is not constant. Maybe we can prove that, and once it's done, that I've done it. Right? So it's done.
So this is general statement for every.
General statement, as long as f prime g is not constant, this goes.
Oh,
Intuitively, a protocol also needs to cover the zeros, not just the ones. So you'd expect that, you know, you need at least something a little more, but that you can actually prove it. But you agree that once I've proven this, it now follows that, you know, this is equal to L. So I've tipped over, which is why I want to do this. In the very end, if the graph has cover number at most k, I have communication complexity at most L plus 2. This L is a number that I've calculated, right? It's this number. Otherwise, it's going to have at least L's. And that establishes production. And all I'm left to do is just do this slight variation on a known, on an obvious, which is also not hard. But
Okay, so for background, that inequality without the plus 1. So that has been known for all parameters.
yes, so this is proof, right? So a communication protocol.
That's just like parameters.
Huh?
That was just like the, you know, trivial everyone doing.
Yeah.
And with the plus 1, it is not proven before.
Well, maybe someone has thought about it, but it's a small proof. It's not gonna be hard. It's just because when you learn it in the book, I don't think they teach it. But if you work a little bit, you get that. It makes a little sense. But it's like a 4-line. Right? It's just that I guess we had an emotional moment when we went through all this trouble, and we really felt that we were on the verge of getting something, and then, poof, and then we were deflated when we just used the standard inequality, and then you say, oh, maybe there's a plus one there, and then there isn't. So let's just do that, and we are done. Here for 2 hours, so we deserve to leave. So, yes, okay, yes. So let's prove it. So the observation is trivial about the plus one, but not immediately obvious without it. So let's prove it. Let's prove it by induction on the following number. Or let's prove it by induction on the obvious. Well, if this is 0, then right, so actually we want to prove this if f is non-constant, right? Otherwise the kind number could be 0, that log isn't really defined. So if f is non-constant, then this is bigger. This is bigger. So now let's say if f is non-constant, this is at least 1. Now suppose that's 0, meaning chi1 of f equals 1. Chi1 of f equals 1, but f by assumption is non-constant. So it's like, something I have like a rectangle somewhere, maybe with many 1s, and elsewhere I have 0. But, well, then I need at least one bit, right? At least so CP and needs to be of n, and we use it down. Which is what we know. Okay, so now suppose, tricky, but let's get there. So now suppose that log I1 of f is equals some small value, right? Now let's take any protocol for it, actual protocol, right? So the protocol communicates something, right? And this splits the matrix into 2, right? And on this subtree, this subprotocol computes this thing, and this subprotocol computes this thing, right? But it always happens that for one of the sides, chi1 of f is equal to d. It can't be less. It won't be more, otherwise this equals 2, but it can't be less. They can both be less. They can't both be less. Yes, they can't both be less. So so for one of them, F1 or let's say Fi. So this guy computes F1, this guy computes F0, this guy computes F1. So for one of them, this equals to D. You need the log of that. Log, sorry. No, sorry. D. Because if they were both less than D, then I could just add 1, and then the chi1 would be at most D, right? But it's not, we're assuming it's D plus. Okay. And now, okay, so okay. So now there's essentially now two cases which you look at, if this number, well, yeah, if this number, sorry, if chi1, not log, but chi1 for fi is actually at least 2, right? So now the only problem is that f might not be constant, right? So, but if this guy is at least 2, then f can't be constant, right? And in that case, by induction hypothesis, the communication protocol for fi, let's say f0, has to have at least d plus 1, but then this protocol has d plus 2. So otherwise, done. So we're done. Otherwise, you have chi1 of f equals 1. Fi equals fi. And in fact, this must be true for both, right? Because this is right. So this is this must be true for both. I think because we're assuming this, and B is now
You can click on the largest.
no, but I actually want to say this for both, I think. For both. Well, maybe it doesn't matter. Certainly, oh no,
His I was not the largest of the two, right? So if K1, if chi of Fi is 1, then chi of F2 of the other one must also be 1. Or, right?
well, right. So I'm going to claim that they're okay, what? I'm going to claim that neither of them can be constant. So neither of them can be constant. Yes, neither of them can be constant. Is that true? No, maybe that's not true.
I guess we need subcases where one is constant, and then a subcase where the other one is constant.
Right. Well, okay. So, look, suppose that let me say that this is true for both. Yeah, because that's what I've written here. I've deduced that at some point, but then assume that this is true for both. No? That they're
If the previous line is referring to the larger of the two, then the next line it can be,
huh?
the if statement. If the Fi over there is about the larger of the two studies,
Yeah.
then
No, wait. Yes, this. You mean? No. So this statement is there exists one of the guys, yeah, such that this equals, yeah, right. And but I want to say that you know, so for the other guy, it can't be all zeros. Right? Because so let's say this is the guy that is large, that has this. The other guy can't be all zeros, because if it was all zeros, I wouldn't, I mean, the chi number at the root would be the same as the chi number here. Right? So this is not all zeros. Okay. So if it's not, and if it's not all zeros, then it must be have chi1 at least 1, right? So for both of them, this is true. Chi1 of f0 is at least 1.
if it's 0 for one side, then this protocol that you've done is not optimal in terms of is that what you're saying?
Right, that's true. That's true, but yeah, exactly. But then it's +1, right? No, what am I saying? No, I just want to say that this for chi1 of f1 is at least, so this would happen for both. Right? Because for it happens for one of them because this is at least 1, right? So the child must be must have 1. But if it only happens for one of them, then actually chi1 is 1. So the stealing of log of chi1 is not at least 1, it's 0. Right? So they must both be at least 1. Now they must both be at least 1. So and now I claim also, so they're at least 1, right? Now I claim also that they're not constant, neither of them, right? Because if one of them is that true, I think is that what I said? By the way? Oh no, they must both be at least 1, and at least one of them is not constant. That's enough, right? So they must both be at least 1, and then one of them is not constant. But then okay. So right, so this always happens. If D is at least 1, right? So I kind of, and then we're done. Right? So if D is at least 1, then log of chi1 is at least 2, right? So that means that this ceiling of the log of chi1 is at least D. And if D is at least 1, then that means that this number is at least 2. And then I'm done. So the only case that's kind of that edge case that I'm missing is the case when D is 0.
Right, that's kind of like the second base, like you're doing this proof by induction. And you have the base step and the induction step. So it's kind of like you should have like a next base step where D
Yes.
is 1.
I guess that's true.
Because somehow on the border from 0 to 1, you actually breaks down.
You're right. So that's actually, that's good. I will rewrite it like that. I mean, that's a lot clearer, right? So you do it for D equals 0, you do it for D equals 1, which is a different argument, and then from then on, you're done. Right? And for D equals 1, which means that the top thing is at least 2. No, the chi is at least 2, not the log. That means that there has to be one guy that's at least 1. And there, no, so that means that they're both at least 1, and one of them is non-constant. And now you apply the previous case. Right? That's it. Right? So there's two cases, like D is 0, D is 1, and D is 2. So if D is at least 2, yes, if D is 0, D is 1, if D is at least 2,
But don't forget that in induction it's D plus 1.
So if D is 0, we're done. D is 1, we're going to do it. If D is at least 2, then this will always happen. And we've done it. So all we're missing is the D equals 1 case. So, or the D equals, no, not the D equals 1 case, but this, right, so sorry, you're right. So this equals 1 case. And for that case, you have to observe that they can't both be constant, right? So, so if this is 1, this is equivalent to chi1 that is 2.
There are exactly 2 rectangles.
It's exactly 2. Yes, you need exactly 2 rectangles. And now you communicate it. Now they both have to be 1, right? Because if one of them is 0, chi1 would actually be 1, not 0. And so if one of them didn't need any rectangles, it's a constant 0 function, so you can do it with 1 rectangle, not 2. You don't need 2. Does that make sense? Yeah, and I think this, or you could get rid of the first one. Thanks. Do it exhaustively. Exhaustively?
Like there are so many functions with 2 events.
Oh, sure.
Anyway.
It's like I'm tired now. I'm saying. But I think that, so if chi is 2 and you have a communication protocol, let's say, now look at both sides. I claim that they can't both be constant. So one of them needs to have chi, I guess at least 1, and they are both non-constant. Because if one were constant and it was the constant 0, you'd be wasting the first round, so it's not a minimal total. Are you still following? I'm not following myself. So
No, I'm surprised that there isn't a more or less technical reason why this is true.
Oh, like a one-shot phrase, that would be great.
Like, we know the log, of.
Yes.
But with plus one now, suddenly we have to go through the calculation.
Yes.
Okay.
Well, I have an intuitive reason for why it should be true, which is Pi1 only counts the ones that you need, but a protocol also needs to do the zeros. That's my intuition for why you might hope for a theorem like this. But then the proof that is like this taken out, right? So, and it kind of makes sense. It makes sense, but then you there's this case and kind of not nice, but I claim it should be something like this. So if pi2, you take a minimal protocol, and if pi of f is 2, right? Then they come. They are both non-constant because if one is it's a middle protocol. If one of them is constant 0, then if one of them is constant 0, then you are wasting it. You're wasting it. What do I mean?
Well, then you still have,
I mean, but you have a whole high here.
Yeah.
Right, so you continue here.
The whole point, you just need to prove that the communication complex is at least two, right?
Yes.
There, and so,
Yes. Then, oh,
so in that case, you still need at least one more bit of communication. I mean, you could not just, and,
if one side is.
and,
Yeah.
there.
if one side is constant and constant 0. What if one side is constant 1? Is that still possible?
If one side is constant one.
You could have 2, right? Because you could have
Yeah.
something like this. And then you have the pattern.
Yeah.
Right?
There's only.
Well, but
It's still not
you still need 2 bits of communication. Yeah, right. So I'm happy with that. It's somewhat else convinced. Smallest detail.
I need to go because I need to give an exam. in 10 minutes.
Sure. Thanks for coming. You. And thanks for super.
Let me know in the next session.
We'll do.
Bye, guys.
Fine, but I think we're done essentially. So that's the whole proof. You've now seen all of it. So I can make some remarks that I make in the paper, which I think are important. So first thing is that we don't get any hardness approximation at all. Right, 0 like this. +1, you lost. So, but Kushilevitz and Weinrev have shown that approximating communication complexity of a given total function is actually cryptographically hard. So you can break pseudorandom generators, say, if you could do that. Up to a factor of 1, sorry. Yeah, so approximating up to a factor of 1.1. And that's the CP of it, not the size of the protocol. The communication complexity is NP hard to approximate up to factor of roughly 1.1. Cryptographic, no, not anything. Sorry, crypto. So we do believe it's hard, right? So we can't prove yet that it's NP hard. That's the first remark.
And no upper bounds. This factor is doable. One factor is doable.
Say again?
One factor is doable like an upper bound.
Oh,
How well we can do it.
no, it's completely unknown. No. I mean, look, if you do that to a constant factor, you'd have essentially created a polynomial time algorithm that would decide.
Right.
I mean, it's like, communication complexity. Oh, I guess it wouldn't give it right. So that would make communication complexity just very easy. You just run the algorithm, look at the matrix. Sure. Kind of you now decide the super polynomial.
But that's within a linear.
Within a linear, right? But suppose that you've proven that it's cryptographically hard, even cryptographically hard, up to not a factor, but up to any exponent. Yeah, up to exponent of n to the c. For all c, right, yeah. Constant fixed c, you could prove that it's crypto hard up to an exponent. Then you disprove the log rank conjecture. If you believe pseudorandom generators, because otherwise you could use computation for the rank, but Ray can use pseudorandom generators.
We don't know that.
Right, it's unknown, and there's some conjecture in their paper, which actually I've tried to work on with these guys, with Shuichi and Rahul. That would give you a square there. But it seems really hard. I mean, we tried to adapt their proof. I mean, it's a beautiful paper. This I must say, it's like one of the. It's really surprising. It's like one of these few papers where they really analyze what the protocol has to be doing, and there's a way of arguing like that, and then but I've tried to apply it on anything else because it's such a beautiful argument, but I could not. So, right. So I don't know. Yeah. Okay. Right. So, but you could conjecture, like, so for instance, vector cover, vertex cover is hard to approximate up to a factor, right? So you could conjecture if you actually want to know the size of the protocol, not the depth, then you could also get such a factor. But then actually the place where we die is this theorem. We have no analog for this theorem somehow. Where if instead of without the log, we don't know how to, and it kind of makes sense because, right, you could conjecture, and that's not true, right? You could conjecture that, the size, the number of leads in the small protocol for F is like at least, what would it be, like 2 times pi1 there? Or even super constant? Like maybe bigger than 1, super 1, bigger than 1? But that's actually probably not true, right? Because, there's some unbalanced, like AND-like protocols, right? That have very small pi1, or that have pi1 close to the number of leads, right? So you have these protocols where Alice communicates and that's a 0, and then Bob communicates and that's a 1, and then Alice communicates and that's a 0, and then Bob communicates and that's 1, so on. They're very imbalanced, but the number of ones in them is actually not huge. Or actually it's actually close to, is that correct? Right, the number of leaves now is well, this is actually fine, but it's not a good example. So what do I want to say? 1. You might have convinced that you could have an argument for that. I'm not sure, maybe it is true. I just didn't think about it. Somebody have to convince it over. So I need to find a specific counterexample, or not say it, or just do it. Okay, so just right. So also like this result is not very robust. Like things like protocol balance. Right, so these issues, whether the protocol is balanced or not, you can always balance the protocol, but there's a constant factor loss now in the communication complexity. And then, if you just want to, ideally the data result will be robust up to this type of changes, and this is not, and right. Yeah. So yeah, so this approximating the communication complexity problem, it's like super vital. Very hard. And I guess it's well, so yes, so we're done. Thanks guys for attending.
For talk.
Thank you, Alexei, all the way from Russia. It must be late. And eventually Alexei will come and he'll in person, and George will also come at least part of the time. There's some budget for him to come. And thanks. I guess we have to decide at some point who's going to speak next, maybe in 2 weeks or something. We could do another one. And I'll see you.